In engineering, ideas become reality through technical drawings, the universal language of creation. These blueprints are the bridge between imagination and the physical world, allowing engineers to communicate complex concepts with clarity and precision. These drawings are more than pictures. They're precise instructions that turn concepts into tangible products. Every line, symbol, and annotation carries meaning, guiding the hands that will shape raw materials into functioning machines. At the core are two essential documents: the part drawing and the assembly drawing. Each plays a vital role in the engineering process, ensuring that nothing is left to guesswork. Think of a part drawing as the recipe for a single ingredient, detailing every dimension, material, and finish required to create that component exactly as intended. And the assembly drawing as the recipe for the final dish, showing how all the individual parts come together to form a complete functional product. Each serves a unique purpose. One defines a component, the other shows how everything fits together. Without both, the path from concept to creation would be incomplete. Understanding their differences is crucial for any engineer or technician. Mastery of these documents is a fundamental skill in the world of design and manufacturing. A single error in a drawing can lead to costly mistakes in manufacturing or assembly. Even a small oversight can result in wasted materials, lost time, or even product failure. These documents ensure everyone speaks the same visual language, binding design intent to the finished product. They align teams, streamline production, and reduce the risk of miscommunication. In this guide, we'll explore what each drawing represents, the key information they contain, and how they work together to bring ideas to life. We'll walk through their creation, examine a real-world example, and highlight common pitfalls to avoid, ensuring your designs are both accurate and effective. By the end, you'll see these drawings as the foundation of every engineered object, the silent architects behind innovation and progress. They are the silent force behind precision, communication, and the act of building. Every successful project owes its existence to these carefully crafted documents. Let's begin the journey from idea to reality and discover how technical drawings shape the world around us. A part drawing or detail drawing is the blueprint for a single component. It's a self-contained instruction manual for manufacturing one item from raw material. The drawing features orthographic views, front, top, and side, showing every detail. Dimensions define size and shape. Tolerances specify acceptable variation. Material type, surface finish, and special requirements are clearly noted. All this information is organized in a standardized title block, giving the part its official identity. The part drawing ensures that anyone, anywhere, can make the component exactly as intended. It's the foundation of precision manufacturing. The assembly drawing shows how individual parts come together to form a complete product. It doesn't detail how to make each part, but focuses on identification and placement. The bill of materials, BOM, lists every component, each linked to the drawing by numbered balloons. This system lets assemblers quickly match parts to their locations. Assembly drawings often include isometric or exploded views for clarity. Sectional views may reveal internal arrangements for complex assemblies. Key overall dimensions help ensure the final product fits its intended space. The assembly drawing is the master guide for building the finished product. Part and assembly drawings serve distinct yet equally vital roles in the world of manufacturing and engineering. The part drawing is a machinist's blueprint, packed with precise dimensions, tolerances, and material specifications, everything needed to create a single, perfect component from raw material. In contrast, the assembly drawing is a technician's roadmap, using item numbers, spatial relationships, and clear instructions to show exactly how all the individual parts fit and work together as a whole. Part drawings are incredibly rich in detail. Every feature, hole, and surface is precisely defined, leaving no room for guesswork during fabrication. Assembly drawings, on the other hand, focus on identification and organization, featuring a bill of materials and balloon callouts that link each part to its exact position in the final product. Visually, part drawings rely on multiple orthographic views to show every angle, while assembly drawings often use isometric or exploded views to make the relationships between parts crystal clear. Each drawing represents a different stage in the process. Part drawings guide fabrication, while assembly drawings direct the construction and integration of components. One cannot function effectively without the other. They are a sequential, inseparable pair, each building on the information provided by the other. Together, these drawings guide the entire journey, transforming raw materials into a finished, functional product through careful planning and execution. This partnership between part and assembly drawings forms the backbone of engineering, ensuring every project is built with accuracy and confidence. Creating accurate drawings starts with a 3D model in CAD software. For a part drawing, model the component in detail, then generate orthographic views. Add dimensions, tolerances, material notes, and fill out the title block. The drawing must contain everything a machinist needs, no guesswork. For an assembly drawing, build the digital assembly, then create an isometric or exploded view. Generate the bill of materials and add balloons to link parts to the BOM. Include key overall dimensions if needed. Complete the title block before releasing the drawing. Every step ensures clarity and accuracy from design to production. The process transforms digital intent into real-world results. Let's see these principles in action with a gearbox pinion assembly. Each component, pinion shaft, gear, bearings, key, retaining clip, gets its own part drawing, detailing geometry, material, and finish. The gear's drawing includes specialized data like tooth count and hardness requirements. Even the smallest part, like the key, is precisely defined. Once parts are made, the assembly drawing takes over. An exploded isometric view shows the order and orientation of assembly. The bill of materials lists every part, with balloons linking each to its place in the drawing. An assembler can follow this single sheet to build the product correctly. This is engineering documentation in action. Even with advanced CAD tools, drawing errors happen. Underdimensioning leaves features undefined. Overdimensioning causes confusion. Incorrect tolerances can make parts too costly or unusable. In assembly drawings, mistakes in the bill of materials, wrong part numbers, quantities, or missing items can halt production. Misplaced or missing balloons lead to assembly errors. Poor revision control is a universal pitfall. Outdated drawings can result in scrap and wasted resources. Every change must be tracked and updated. Rigorous checking and disciplined revision history are essential. Attention to detail prevents costly mistakes. Good drawings are the result of careful, systematic work. Clarity is king. Keep drawings clean and easy to read. Arrange dimensions logically. Use section and detail views for complex areas. Design for manufacturability. Consult with machinists to ensure practicality. Peer review every drawing. A second set of eyes catches hidden errors. Use standardized checklists for thorough reviews. Always update the 3D model first, then the drawing, never the other way around. This keeps everything in sync and prevents discrepancies. Embrace the single source of truth, the 3D model. Discipline and collaboration are the keys to reliable drawings. These best practices ensure quality from design to production. Part and assembly drawings are more than just technical documents. They're the language of creation, the foundation upon which every engineered object is built. These drawings are the silent communicators that bridge the gap between imagination and reality. The part drawing is like a recipe for the building block, detailing every measurement, material, and feature needed to bring a single component to life. The assembly drawing, on the other hand, is the blueprint for the whole, showing how each part fits together to form a complete, functioning system. Together, these documents turn ideas into reality, ensuring precision, clarity, and consistency at every step of the engineering process. These documents empower machinists and assemblers, reduce costly errors, and enable seamless global collaboration across teams and borders. Mastering them is a rite of passage for every engineer, a crucial skill that unlocks the ability to innovate and solve real-world problems. It takes skill, patience, attention to detail, and a deep sense of responsibility to get it right. Every line, symbol, and notation has real-world impact, guiding hands and machines alike. Drawings are the bridge from concept to product, transforming digital visions into tangible objects. They are the enduring record of human ingenuity, capturing generations of knowledge and progress. These documents tell the story of how we build our world, one detail, one drawing, and one innovation at a time. This is the true language of engineering, a language that shapes the future.